Hey guys, welcome to part 1 of our chapter 4 dynamics study. So we're going to get through most of chapter 4 before our Thanksgiving break, before our trimester 1 finals. So we follow along with the book kind of, but most of the materials in there, I break up a little bit of the questions so that we have a little more, we get a little more experience in solving some of the tougher kinds of questions. So let's go ahead and dive right into this. We're talking about Newton's laws of motion, the first, second, and third laws. And when we talk about forces, we're looking at dynamics. That's what we call dynamics in physics. So the first thing we look at is what is a force? And while we wish we were all Jedis, a force is a simple push or a pull. That's all a force is. It just pulls or pushes something, and depending on what the source of the force is, determines whether it's a push or a pull. The units of force is a Newton, so capital N Newton. We use the N, and the actual units is a kilogram meter per second. More on that later, but remember this is a mass, and that is an acceleration unit, so that's kind of interesting. So there's 4 fundamental forces that make up all the forces in the universe. We're going to be talking really about gravitational and electromagnetic, but here are the types of forces that we actually deal with in physics. There is gravitational, and that is the gravitation due to large bodies of mass like planets, like moons, like black holes. Those are pretty cool. And then we have these 2 things called strong nuclear and weak nuclear. So these are the stronger of the forces, the fundamental forces that we deal with. Strong nuclear binds protons and neutrons together. Those are responsible for making up the atoms that make up the matter that we're familiar with. And weak nuclear, while stronger than gravity, it's not the strongest nuclear force, hence the term weak. Stronger than gravity, but it's kind of responsible for radioactive decay and when elements decompose into different other elements. The last type of force that we're going to be working with is the electromagnetic force. It's responsible for really lots of things, but force between charges, the forces that objects experience in terms of magnetic fields, that is a pretty standard thing, especially if you take a second-year physics course. You'll talk a lot about the electromagnetic force. But once again, we're mostly talking about the gravitational force and then frictional forces that happen due to electromagnetic force between particles. More on that a little bit later. But for the force of gravity, we have this really interesting thing. It's always attractive, seems to have an infinite range, and is proportional to mass. So that always attractive part, that's actually pretty interesting. Basically, it's always a pull of some kind. It's always going to pull objects towards itself. The infinite range and proportionality to mass, we're actually going to study a little bit later in more detail. But basically, the more mass an object has, the more gravity it has to have. More on that a little bit later. But for us, we know that it's always going to pull on objects down. Proportional to mass. Now remember, mass is simply the amount of matter an object has. Amount of matter. It is a kilogram, and remember, it stays constant. In other words, the amount of mass an object has doesn't change based on its location, while the weight of an object can. So the weight of an object is simply the force of gravity on the object. Gravity on a body of mass. And so that can change based on the amount of gravity something has. If it's on the moon, for example, it's about 1/6 the gravity of the Earth. The Earth acts at 1 g, or 9.8 meters per second squared. Jupiter is something bigger. I think it's closer to 25. So depending on where the object has, the weight can change, but the mass has to remain constant. Okay. The formula, I know we were all excited for that, but the formula for the force of gravity is pretty simple. It's Fg equals mg. We've probably seen that around a little bit. You also can see written as this, as the weight of the object. Weight is equal to mg. You can also see ma sub g, or that is simply the acceleration due to gravity. And so once again, just kind of pay attention to the units. This is a kilogram thing accelerated, which is a Newton. So all of these are measured in newtons as we do that. A quick note on G here. G varies depending on the mass of the gravity-causing thing, planet, moon, whatever. The distance the object is from the center of that thing, and that has to deal with what we call the field strength of the gravity-causing thing. And once again, this is one of those things that we'll talk about a little bit later in the spring, but the field strength is actually a thing that ends up changing, and a lot more details on that. So a quick calculation question. Let's determine your weight on Earth, Moon, Jupiter in newtons. And so let's see. Okay, so we are on Earth, and we know the acceleration due to gravity on Earth is about 9.81 meters per second squared. Okay, cool. The first thing we want to do is we want to get pounds to kilograms. And what you do is basically you just divide by 2.2. So here's my weight, 265 pounds, divide by 2.2 to get about 120.5 kilograms. So the weight on Earth, W sub E, is mg. So 120.5 times 9.8. So for me, I get about 1181 newtons. So I just want us to kind of look at that number. That number is way bigger than what you weigh on Earth. A couple of reasons for that is you kind of ask yourself, is a Newton a large force or a small force in terms of how we think of it? Seems to be pretty little. On the moon, we do the same calculation, but on the moon, it's about the sixth of Earth's gravity. So its acceleration due to gravity is about 1.64. Once again, the mass remains the same. So weight on the moon is m times g. The mass remains the same. Gravity is the thing that changes, or the acceleration due to gravity. So the weight I weigh on the moon is about 197.6 newtons, way smaller, or about sixth that of the Earth. Kind of cool. Take a look at Jupiter. Based on how you estimate things, we know the gravity, if we were to able to stand on the surface of Jupiter, gas giant, kind of weird, it's about 25 or 24.79 meters per second squared. So way bigger than Earth. The weight, once again, is mg. So 120.5 times this 24 number. So the weight on Jupiter is about 2987 newtons. So once again, just a quick example on how the weight of the object can change. However, the mass remains the same in all of these things. So once again, mass here, mass here, mass here. Weight changes, mass stays the same. Okay, good. So I know we've all heard G forces. Maybe we've seen the Marek movie and they're pulling G's. And what that means is the amount of perceived gravitational force you feel. So 1g, the acceleration of 1g is 9.8 meters per second squared, approximately 9.8. We just talked about that. My weight on Earth, remember, was approximately 1180 newtons. So if I'm experiencing 1g, you're experiencing normal Earth conditions, 1180 newtons or whatever you normally weigh. So when you have a g-force, what it's talking about is how many times the force of gravity does the object feel. So here's a quick question. You have a car accelerating at 4.8 meters per second squared. How many g's is that? Well, you'd get whatever number you're looking at, divide it by about 9.8, and I get about a half a g, or 0.49 g forces you feel that. So not one full g. Okay, cool. So during a rocket launch, SpaceX launch, for example, it accelerates at 28 meters per second squared. How many g's is that? Well, same way to calculate that. 28 divided by 9.8. And here we get about 3 g's, or 2.9 g's, that you can handle that. So, all right, a normal human can withstand about 4 g's. This is without training. And so we have, there's maybe some cool videos we can look at, but fighter pilots undergo a lot of training to be able to handle these types of G's, basically just working out to make sure we get that done. So at 4 G's, if you run the numbers, that is experiencing an acceleration of about 39.2 meters per second squared. So that's pretty substantial. At 9 G's, close to what the upper limit of what we think humans can handle, at about 9.0 G's, that means it's close to 88 meters per second squared. So when we're looking at these numbers, we're looking at how the forces feel like that. So once again, this is close to 9 times the body weight of that. So those numbers get really big really quickly, which is kind of cool. So a few more examples on that when we get to class. So the next thing we want to talk about is Newton's first law of motion, or inertia, which is kind of cool. So we have this really weird thing. We don't know a lot about inertia other than it's connected to mass somehow, and we can't really explain, with all of our tech and everything, we can't really explain other than these really simple rules. So Newton's first law, I know we're familiar with it. An object in motion will stay in motion, and an object at rest will stay at rest unless acted on by an outside force. And I think we've all kind of heard that before. One of the things I really want to add to this is we're going to say an external net force. So external keyword here, net force, we're going to really dive into what that means here. This is also referred to as the law of inertia. Basically, things want to keep moving at a straight line, constant velocity, unless acted on by that net external force. So unless something else hits it, if this thing is moving in space, it's going to move in a straight line at a constant velocity unless something else knocks it out of the way. So a couple of 3 times you notice your inertia. So imagine you're on a racing track and you feel it 3 times. Essentially, you feel the first time is 1 when you start, when you stop, and when you turn. So we have these 3 different things, like when you start, you feel like you're being pushed into the seat. When you stop, you feel like you're being pushed forward. And when you turn, you feel like you're being pushed to the side by some phantom force, which is kind of cool. So another way of thinking of Newton's first law is that there's no net force on an object, no net force here, it will stay at a constant velocity. If it's not moving, it has a constant velocity of 0. So that's a really great way to think about that. So we'll have a few more examples on how to handle the inertia of the thing when we talk about our problem set next class. A couple things we need to look at is what we call the support force or the normal force. And we're going to talk about this subject a little later on, but we have this thing called a free body diagram. And what it does is it's a way to describe forces acting on an object and able to compare them, and we can throw some math at it and all that. But let's say, for example, that my block is sitting on the surface, the bottom of the box there is the surface, and I have the force of gravity will always be acting down. There's my Fg. Well, my normal force, Fn, that is the supporting force. That's what the floor is doing. Because my object doesn't fall through the floor, there's a supporting force. That's what the normal force is. If it's just sitting there, I know that these guys have to be equal in magnitude. And sometimes we can draw, like we did in geometry, little lines indicating that. That just lets me know that they are equal. Everything is balanced. So it's just going to be sitting there. Okay. But if you drop that same block or same book and let it go, I have only one force acting on it. This is now an unbalanced situation. This object would then have to accelerate downward. And anytime something accelerates, it has to accelerate in the direction of the unbalanced force. Another way to say that is it accelerates in the direction of the net force. So we use the term sigma F. That means everything added in the direction. So that means the net force of the object. So that's what the normal force is. And so we have a couple examples here on our notes. Have a couple of demos to show you guys also. But Newton's first law is when things stop suddenly and it feels like things slide forward, that's what's happening is the object is experiencing its inertia. When the stuff slides forward in your car, when you come to a stop really quickly, it's not that there is a force doing it, they're trying to do the thing they were doing before you tried to stop. So headrests are put in cars. When you get hit from the behind, your head wants to try to remain stationary, but the car moves forward suddenly. So those headrests kind of keep you from jumping forward and sustaining injury. So a lot of safety features that used to not be in cars, kind of cool. One of the last things we'll talk about here is how to quantify inertia. Quantify is how to put a number to it. Well, the easiest way to say that is the object's mass. The more mass an object has, the more inertia it has. You can also say its tendency to resist changes in its state of motion is greater with more mass. So mass tells you how much inertia it has. If it has more mass, it has more inertia. If it has less mass, it has less inertia. In other words, it's simply harder or easier to move based on the amount of mass the object has. Kind of cool. The next chunk of stuff we'll talk about is Newton's second law of motion. This is the more famouser of the laws. We all kind of know this F equals ma thing. Newton's second law is pretty simple. It basically says, it's like the law of acceleration. An object is accelerated in the direction of the net force, or a net force causes a mass to accelerate. All of the things, it's basically the law of acceleration. So the formula is this: net force equals ma, where this sigma F means it's the net force. The m is the mass in kilograms. And the acceleration in a meter per second squared. So remember, once again, note the units. It's a kilogram meter per second squared, or capital N Newton. So law of acceleration. So we're just kind of going over the basics today. Don't worry, we'll have way more fun with these problems a little bit later on. Just to give a quick rundown on how these questions work. Have an example here, 5 kilogram block, frictionless track. So we like frictionless right now. It simplifies what we have to do. So now we have a mass of 5 kilograms, a force or a net force of 10 newtons, and we want to know its acceleration. So pretty simple equation at this point. 10, 5, and A. So we get about 2 meters per second squared. So that is the acceleration this particular object would feel. Okay. Remember, force is a vector quantity. And we know that because acceleration is also a vector quantity. So for this particular question, we know we have a mass of 650 kilograms. Acceleration, here it gave me 4.0 meters per second squared south. That could have been negative, I'm not sure the context of the question, but for these simple ones, we're just kind of roll it like this. Net force is mass times acceleration. Here, the 650 kilograms, the 4 meters per second squared. So I get a net force of 2,600 newtons directed to the south. If I would have used -4 to indicate the south or down direction, I could have written negative up there. So it really depends on how things are set up and the nature of the question. Another kind of question we have, we can apply kinematics to these. So I have a 1,500 kilogram bowl of banana pudding. It accelerates from rest, so V naught equals 0 meters per second. And then I have a final velocity of 45 kilometers per hour. Make sure we know how to convert that to get 12.5 meters per second. The time this happened in is 8 seconds. And we want to know what force was. So the connecting thing between the kinematics sections we've been studying and this dynamics is kinematics was an object was moving. We just don't know what caused it to move. Dynamics basically it answers that question. A particular force accelerated the object to do something. So we're starting to tie many things together. For this question, I would use the first kinematic to figure out what the acceleration was. So 12.5 equals 0 plus acceleration, that's what I'm looking for, times 8. So the bowl of banana pudding is accelerated at 1.56 meters per second squared. I can then use my net force equation to plug in the mass and the acceleration to get a net force of 2340 newtons acting on the delicious treat. So what happens if I have one or more force acting on the object? So when forces work together, I can basically start off with my free body diagram. Here's my little block right here. And when we quote unquote work together, that means the two forces here are acting in the same direction. And thinking back to my original equation, I have net force is mass times acceleration. And when we start getting to these problems that more than one forces are acting on the object, the net force basically asks the question, what combination or what interaction of forces is causing the net force? Or what combination of those is causing the mass to accelerate? So one of the first things we have to do is figure out what is causing the net force. In this case, because they're both F1, F2 are pointing to the right direction, the positive for us. We say F1 plus F2. We can then pull these guys together and say that F1 plus F2 is equal to MA. So all I did is substitute that. So I could be looking for either one of these quantities based on how the question is worded. If I break it down to all of its components, it makes it easier to figure out what's going on. So what if I have a few more forces acting on it, or let's say I have some different combinations, F1 and F2, and then I have F3 pointing this way. We still look at net force equals mass times acceleration. Here, the net force is a combination F1, F2, and F3 is acting in the negative direction. When I substitute everything together, F1 plus F2 minus F3 is equal to MA. So once again, based on how the question is worded, we have combinations of things that we can determine based on what's given, what's unknown. Oftentimes, the difficulty of the question is basically determined on what you know and what you don't know. The last chunk of info we'll study or work on for today is Newton's third law, the famous action-reaction force. So before we get into how we define it, let's ask the question, how does a fish swim through the water? So mechanically, right, what we have is the fish pushes on water. The reaction to that is the water pushes fish. Interesting. So in order for the fish to actually move, if the fish is going to push on the water with his fins or whatever, the water actually has to push back. That will propel him forward. Well, how does the rocket rise in the air? Well, essentially what happens is the rocket pushes the gas out. The exhaust gases. That means the gas must push against the rocket. That's why rockets work in space. The mass expelled from the gas is creating a force that is equal and opposite, and so it pushes back on the ship that makes it go forward, which is kind of cool. So what happens to the bug hitting the windshield? Well, this is a pretty classic question here. We know that there's an action-reaction force, and I want us to look over here at this piece right here. The action-reaction force, that means there's the same force, but it acts on different objects. That's interesting. Well, first off, we know that splat, the bug hits the windshield. So we know that the forces that the bug and the windshield experience are the same. So Newton's third law tells me that. But what happens is the acceleration that the bug feels is huge, while the windshield is accelerated very minimally. And I want to ask you, why? So this law is sometimes paraphrased, to every action there is an equal and opposite reaction. But once again, this is a valid statement, but an important fact to remember is that the action-reaction force are acting on different objects. I should say on here. So the best example of this is your weight. What causes your weight? Well, the earth pulls you. If we use the same format that fish push on water, water push on fish, if earth pulls you, then that is right. You actually pull the earth. Interesting. So one of the main takeaways to this is that the weight is not an action-reaction pair. So to describe action-reaction pairs, I have a couple of little things down here. So identifying action-reaction pairs, ball pushes glove leftwards. What would be the action to this guy? Bowling ball pushes pin leftwards. So I want you guys to fill these in, figure out what's going on there. And this diagram here at the bottom, it's a pretty cool diagram. It's a really nice way to illustrate what's going on. So I want you guys to identify 6 pairs of the action-reaction force pairs in the diagram. So I'll give you a couple. So here's the first 2 I gave you guys. Tractor push ground, ground push tractor. And so what we would do is we would kind of F12, F21 is how we would say that. Tractor pull rope. So here we can say this right here. We could say force of tractor on rope. And then we have this one. This is force of rope on tractor, or vice versa. So your job is to go through and find at least 4 more. There's a bunch in this diagram, but we have the tractor and the elephant and the poor guy suspended in the middle. Wonder what he did wrong to deserve such a fate. But here is part 1 of Newton's laws of motion. So we didn't do lots of math. We're just going to do lots of explaining. So your homework assignment when you guys come to class will reflect that. All right. Let me know if you have any questions. And thanks for watching. Okay, thanks. Bye.